Okay, so today we're going to continue with the study of second-order differential equations. And remember, we have the general framework of solving any linear ODE by the two-step method, right? Dealing with the homogeneous part of the problem and then with the particular solution. So this section focuses on the second part of this step, of this process, finding the particular solution in order to finish solving completely the non-homogeneous problem. So remember, in the previous section we dealt with the homogeneous problem when f of t was 0. So take your time with this section, because although it's not overly difficult, there are lots of misconceptions in the beginning, so you just have to make sure you understand carefully how the method works. So the method of finding the particular solution is called the method of undetermined coefficients. There are many methods, but that's the only method I will go over in this class. So before I describe the method in a general setting, it's better to actually go over an example. Many lessons actually are better off started with an actual example rather than the general framework, because then it may sound harder than it is in reality. I should warn you that if you don't have the formula sheet in front of you, pause the video and have it in front of you. One of the entries in the formula sheet is the guidelines of how to find the particular solution in cases like this. So with that in mind, just so you know, the first step of the problem is already covered in the previous sections, right? So normally what you do is you solve the homogeneous part of the problem first. So this is the first thing to do. In some problems, this might be given to you just to speed up the process. But if not, if you have to solve this example from top to finish, then obviously the first thing to do in all cases is to deal with the homogeneous part of the equation. You also have formula sheets for this, right? So remember how to solve this. Well, you take the characteristic equation in R and you solve it, and depending on the nature of the roots, then you provide the solution. In this case, notice we have two distinct real roots, 1 and 2. And so the homogeneous part of the solution is c1 e to the t plus c2 e to the 2t. That's just the homogeneous part. So now we come to the core of the problem on how to find the particular solution. So how do you find yp, which is a particular solution for the full problem? So the method I'm going to talk about deals only if the non-homogeneous term has a specific form. We're going to write that down immediately, the general description of this format. But roughly speaking, the method works if your terms in the right-hand side of the equation are combinations of a set of functions that are the same, more or less, when you differentiate or integrate them. So for example, exponentials, if you differentiate them, you end up with exponentials, same exponential, with different coefficients, right? But e to the 3t is going to be there forever. So no matter how many times you differentiate or integrate e to the 3t, the constant may change, but otherwise e to the 3t remains there. Polynomials are another category of functions. If you differentiate t to the n, then you end up with another polynomial, t to the n minus 1, right? But same type of function. And sine and cosine are another example of functions that if you differentiate them repeatedly, they bounce back and forth through the same formats, right? So sine prime is cosine, cosine prime is minus sine, and so on and so forth. So the idea is that I can predict that the particular solution, so the stuff that I have to plug in here to match the right-hand side, should have more or less the same format as the non-homogeneous term. So really, if I were to summarize in one sentence the whole method, is to say just the way f of t looks like, that's how y of yp, the particular solution, should look like. Now that's like a vague guess, right? So you have to make sure when you choose yp, you take it in its most general form, but still similar to what you have there on the right-hand side. So in this case, I notice that the right-hand side contains an exponential and a linear term. Although it's just 2t, maybe yp should contain a full linear term. So you have to choose yp in its most general form, and that's the key thing, right? Similar to f of t, but in its most general form. So yp will be similar, let's write it down, similar to f of t in its most general form. That's the key thing, right? I mean, one of the mistakes people make is to take it not general enough, right? And of course, with coefficients to be determined, we don't know which coefficients will match. We will determine that through the process. So in this case, I'm going to choose yp to be a constant e to the 3t. Now notice e to the 3, I mean 3 has to be there always, right? Because that doesn't change via differentiation. The constant may change, but not the exponent of e to the 3t. And then corresponding to 2t, I'm going to use a full linear term, bt plus c. So basically, this is where the method of undetermined coefficients title comes from, right? I mean, by choosing this format for yp, you involve coefficients yet to be determined. And how do you determine them? Well, you're going to just differentiate this. You're going to plug in this format into the ODE, and you're going to match some equations. I mean, you're going to extract some matching equations by setting the coefficients of each of these components equal to each other. So the left side should be equal to the right-hand side. One tedious step here is that you have to make sure your differentiation is correct. You need to differentiate, obviously, yp twice in order to plug it in on the left side. So yp prime is 3a e to the 3t plus b, and then yp double prime would be 9a e to the 3t, and then plus 0, right? Because the derivative of b is 0. So now you're going to carefully plug in these guys into the ODE. So let's do it over here. So I'm going to plug in yp double prime minus 3yp prime plus 2yp equals 4e to the 3t plus 2t. And carefully plug in and make use of parentheses if necessary. So yp double prime is 9a e to the 3t minus 3 quantity yp prime, which is 3a e to the 3t plus b, and then plus 2 the whole yp, which is a to the 3t plus bt plus c. And this should match the right hand side, which is in my case 4e to the 3t plus 2t. The left should be equal to the right, and you do this by matching the coefficients together. So once you plug it in, try to be more efficient. You don't need to simplify on the left side too much. What you gotta do is to write the matching equations for each of the coefficients. So all the coefficients that depend on t, and notice you have essentially 3 types of coefficients. Coefficients of e to the 3t, coefficients of t, and maybe a constant term. So the constants from left to right should match. The coefficients of t from left and right should match. The coefficients of e to the 3t should match left and right. If you do this correctly, you should end up with as many matching equations as the number of unknowns. So the method should provide you enough equations to determine a, b, and c. And then it's just a matter of making sure you don't miss any of the terms. So let's look carefully. E to the 3t, the coefficient only, comes from 9a, right? Imagine you pull out e to the 3t. Then there's minus 9a coming from the middle term, and there is 2a here. So combined, these are the coefficients of e to the 3t, and those should match the coefficient of e to the 3t on the right, which is 4. So notice it can be quite easy. I mean, in this case, you can determine a right away. In other cases, you may just end up with a more complicated system in a, b, and c. Very important remark, for this particular class, I will avoid systems that are too complicated to solve. Because, I mean, you can end up with lots of constants to determine, and you may need to, I don't know, use like in linear algebra, right? Row reduction or stuff like that. So I won't give you examples in the exams that may lead to that situation. So you should be able to solve these equations via substitutions or something very similar to that. Notice also the coefficient of t appears only in one position. That's the only place for t on the left side. So that's 2b. And this should be equal to the coefficient of t on the right hand side, which is 2. Then you have a bunch of constants left over here. So you have on the left minus 3b and 2c. And on the right hand side, the only constant, right, is 0, right? The fact that there is no constant, it means the constant on the right is 0. So this is pretty straightforward. The first equation gives me a equals 2. The second equation gives me b equals 1. And I can plug in b equals 1 into the third equation and then solve for c. So c is 3 over 2. So you just determine the particular solution of this problem. So yp would be a to the 3t, which is 2e to the 3t, plus b times t, which is just t, plus c, which is 3 over 2. So that's the particular solution. Now remember, that's just half of the solution, right? So the full solution of the problem, so the full general solution of the ODE that we started with, is the homogeneous part plus the particular solution that we just determined. So the homogeneous part in my case is what? We wrote it here, so c1 e to the t plus c2 e to the 2t, that's yh, and then plus the particular solution 2e to the 3t plus t plus 3 over 2. So that's the particular solution. So there are more details to discuss in this class, so hold your horses. But in a nutshell, this kind of covers, the essence of the method here. Very important, if your problem is an initial value problem, as with all problems, you do that at the end. So when you try to find C1 and C2 from an initial condition, don't forget to take the full general solution, not just YH, to find C1 and C2. So for example, let's say this problem also gave you that y of 0 was, let's take an example here, 3 over 2, to make it numbers a little bit easier, and y prime of 0, let's say, was a 0. So if you have an initial value problem, you have to involve the full solution here that we just found. So again, might be tedious a little bit, but you have to be patient. We need to differentiate it one more time, because we have to plug in 0 for the derivative of the full solution. So in this case, y prime is c1 e to the t plus 2 c2 e to the 2t. The derivative of this is 6 e to the 3t plus 1, and 3 over 2 goes away. So now when you solve for the initial conditions, y of 0 is what? Well, y of 0 is c1 e to the 0, so that's c1 plus c2 plus 2, because it's e to the 0, plus 0 plus 3 over 2. And this should be equal to 3 over 2. See, that's why I chose y of 0, 3 over 2, so I can have some nice cancellations there. And y prime of 0 would be c1 plus 2c2, and then plus 6 plus 1 equals 0. So 3 over 2 cancels, and this gives me a nice little system here. I think we can write it here. We have c1 plus c2 equals minus 2 if you move it over, and c1 plus 2c2 minus 7. Do a little elimination. So let's say subtract the first from the second, and that gives me c2 equals minus 2 minus negative 2, which is minus 5. And c1, if you plug it in right here, so minus 5 over there, it's 5 minus 2, that's 3. c1 equals 3, c2 equals minus 5. So if you have an initial value problem, then the full solution in this case would be, that's out of range. So the full solution would be C1 e to the t, that's 3 e to the t, plus C2 minus 5 e to the 2t, and of course the particular solution that is stays the same, 2 e to the 3t plus t plus 3 over 2. So this is again if you have an initial condition. If you don't have an initial condition, of course your solution is just this, right, with C1 and C2 arbitrary constants. If you have an initial condition, you deal with it at the end of the problem, and in this particular case you have this. So before we move on to the second part of this lesson, again we're going to have to discuss a little bit more details than what we just talked about here. One important remark is that when you have sine and cosine combination on the right hand side, they have to be taken together. So if your f of t contains sine or cosine or both, right? So I mean if f of t, let's write it here. So if f of t contains some combination, let's say a sine of omega t plus b cosine of omega t. I'm using the notation in the formula sheet. Omega is just a constant that denotes frequency actually in some applications, as you will see later. But if f of t contains a combination of this, then yp should contain both sine omega t cosine of omega t. So you think of this as a single combination in itself. So even though f of t may contain only one of them, think of it as a combination of both sine and cosine, because it's likely that the particular solution needs to contain both. So in fact, let's look at an example right away. So suppose, for instance, that f of t, right? So your ODE, we should probably do this on the second part, but let's see if your ODE contains let's see, sine of t plus t. Right, so we're going to solve this example on the second part, but let's comment on how you choose the particular solution first. So one common mistake is people say, well, if it's sine of t, I'm going to just use a combination a sine of t plus, like before, a linear term corresponding to t. That is incomplete. That is incomplete because it's likely that the particular solution needs both sine and cosine. So pause for a moment and think about from a logical perspective. You have two derivatives here. If y contains just sine, that doesn't mean cosine doesn't happen here, because y double prime will if y contains sine, y prime contains cosine. If y contains cosine, y prime contains sine. So for the matching to occur, whether you have both sine and cosine on the right hand side, it's likely that a particular solution needs both sine and cosine. So rather than this, right, your particular solution should be a full combination sine and cosine of the same t, and then a particular a linear term bt plus c. So whether you have both or not, you should always have a combination of both sine and cosine. So in other words, here's another example. If y double prime minus 3y prime plus 2y, let's say, equals 7 sine of t minus cosine of t, then of course this is pretty obvious that yp will be a combination of sine of t cosine of t. My point is, even if f of t doesn't contain one of them, yp should still be in the same format, a sine of t plus b cosine of t. Whether this contains one or both, yp should contain both sine and cosine. That's why in the formula sheet, and it's very important at this moment, again, if it's not clear, to pause and look carefully to understand what I'm talking about. That's why in the formula sheet, the entry, there is no single entry for sine separated from an entry for cosine. They appear together. You think of sine and cosine as always in a combination like this. So for each combination that appears in the right hand side, you have a combination like that on the right hand side. Again, if it's confusing, when I wrote here sine of t, really think of that sine of t as sine of t plus 0 cosine of t, right? I mean, even cosine is absent, you can still consider it as part of a combination between sine and cosine. So in the next part of today's lecture, I'm going to solve fully this example, just to see how it looks like. I'm going to explain one exception case, which is called the duplication case, and then we're going to finish with more examples on how you choose actually the format for YP, because in many problems you will not be asked to actually compute the coefficients, but you will be asked to actually choose the correct format for the particular solution, and maybe leave it like that without coefficients to be determined. So stay tuned for the second part.